All right, class. In today's video, we're going to talk a little bit about this topic of current. Specifically, we'll get into these two different types we call like AC current and DC current. Before we do that, again, just kind of a quick thing about what this current is actually measuring is it's really figuring out kind of how much charge is flowing through our wire within our circuit in a given amount of time. So we kind of have this measurement, basically say our current, we're going to be using our variable I to represent current. And we're going to be measuring this current in terms of amps. So uppercase A will be our unit. So the way we figure out kind of the amount of amps flowing through a wire is we take the amount of charge that is moving through the wire, which again, we're going to always measure charge in terms of coulombs. We're basically taking the amount of coulombs and we're dividing it by however long it takes that amount of charge to flow through. So we'll be measuring our time again here in terms of seconds. So what's happening is if we were to look inside of a wire, let's say we've got some sort of cylinder tube here representing our wire, right? Inside the wire, we basically have all of these electrons that are flowing through what's most likely our copper strands. So we've got all these little charges, these electrons that are going to be moving. And let's say maybe they're trailing down kind of to the right here, moving through our wire. What our current does is it basically takes some point along our wire. So maybe we're looking along this dashed red line here, and we're basically saying how much charge passes through this line per second. Right? So the faster our electrons are moving through our wire, basically means the more charge is passing this red line per second, we have a higher current. Again, the quicker that these electrons are going to be moving. Now with an actual wire, right, there's basically trillions upon trillions of available electrons that can be moving, so we can have a very large number of electrons traveling through our wire to kind of get whatever current that we might need for our circuit. Now when we think about these ways that we can apply this is, let's say we're trying to figure out, right, how many of these actual electrons are traveling through a wire based upon its current. So with this, again, even though we refer to charge as kind of this moving, we oftentimes show it as being positive charge, right? It's really the electrons that are what moving in these cases. So we can say with our equation, right, if our current is equal to the amount of charge we have divided by the time it takes the charge to go through. Right. Based on this scenario, we're told we have this 2.5 amp current. Right, that's going to be equal to some amount of charge flowing through a wire. And again, for 1 minute, right, we always want to use seconds instead, so we'll say we have 60 seconds within this 1 minute. So if I want to solve this to figure out how much charge is actually flowing through our wire, right, we can just multiply 60 both sides. What we get is that we're going to have a movement of 150 coulombs of charge passed through our wire every minute. But we're not actually interested in the amount of charge that's flowing through, right? We want to know how many electrons are actually traveling through this wire. What's the physical thing that's making up this 150 coulombs of charge? So we can kind of go back to a relationship between our number of electrons and our total charge. So basically we're going to say that our total charge, this Q that we have, right, that's basically going to be equal to the number of electrons we have multiplied by the charge of one electron. So here again, we're saying the total amount of charge we have is 150 coulombs. Right, we're basically trying to figure out, right, how many X number of electrons do we have? And for our charge of one electron, since we typically consider current to be a positive value, we're going to be using just kind of the size of our charge of one electron, which is going to be our 1.6 times 10 to the negative 19 coulombs. Again, so even though electrons are negative, right, we're just using the positive of this number. So we want to here solve for x, get the actual number of electrons we have. We're just going to have to divide both sides by this 1.6 times 10 to the negative 19. And when we do that, that's going to give us a value of a very large number of electrons. We're going to have 9.375 times 10 to the 20th electrons. So again, this kind of number, right, equates to trillions upon trillions of electrons flowing through this wire in a given minute to kind of get us our 2.5 amps of current. Now, when we actually kind of make use of this electric current, there's actually going to be two different types. We have what we call DC current, and we have AC current. Again, if you're familiar with the rock band AC/DC, this is actually where they get their name and kind of logo from. But basically, we have different currents that we use depending upon what the application is of them. So, for instance, if we have something like where we want to charge something with a battery, right, that's different than how current comes out of our wall outlet. So this first type of current we have is what we call direct currents. Basically, the key thing with our direct current is that our charge, it only flows in one direction. So that's kind of like what we had with the picture above of those electrons moving through the wire, right? All of our electrons move in the same direction as they flow through. Now, this ends up being really good if we only want the charge to move over a very short distance. It's kind of the easiest for us to wire. And what we do with this is if we have some sort of small scale application, something like a TV remote that's being powered by a battery, right? Basically what happens is that battery can move our charge in one direction over a very small distance. As we move charge over longer and longer distances, though, what ends up happening is that we end up losing a lot of energy in the process. So by losing energy over the long distance, it basically means it's a very inefficient way of moving our electric charge. But again, any sort of small appliance uses like a double or single A battery. We're basically making use of this direct current. Alternating current, on the other hand, what happens is instead of our current flowing only one direction, it's constantly switching the directions it's moving. So we can kind of think of this as like someone who takes like 2 steps forward, then 1 step back, 2 steps forward, 1 step back. Again, eventually over time they do move forward overall, but it takes a little bit longer, right? It's this kind of constant back and forth movement. So right, if we take these 2 steps forward, 1 step back, right, and then we kind of keep repeating this process forever. What's happening is every second this is basically happening hundreds and hundreds of times, right? This change in direction happens very, very quickly. But again, over time, our current can still kind of move forward and move along the wire, kind of get to wherever its end destination is. So this is something that we're able to move much greater amounts of energy, a lot greater amount of currents here. And this is good for moving over a bigger distance. So if you've ever been driving along the road, you kind of notice that these power lines running along the length of the road, those power lines are carrying alternating currents, which is kind of what our modern electrical grid is made out of. So when that electricity kind of gets from our power lines, goes into your house, and then goes into our wall outlet. Right? That electricity that's coming out of our wall outlets is this alternating current. Now, back in the late 1800s, there's kind of this big debate going on between should we set up our electrical grid with this DC current, or should we set up our electrical grid with AC current? So there were a couple kind of key, very famous players in this debate. So Thomas Edison, kind of the inventor of the light bulb, he was in favor of using DC current. Now, the one drawback to this was, again, because DC is only good over short distances, if we wanted to power an electrical grid of an entire city, what we would basically have to have happen is every mile or so there would need to be like a power plant or a power station to produce that power. Right, alternating current, even though we typically send current at much higher voltages this way, it is able to kind of travel a longer distance. So eventually, this guy, George Westinghouse and Nikola Tesla, they were big proponents of alternating current. They ended up winning out in this kind of debate back and forth between the two. So our current system kind of basically uses a hybrid approach. Right, so basically we have our alternating current moves our electricity from a power plant to our homes. Again, this is kind of what our modern power grid does. And then once that alternating current comes out of our wall outlet, what we then do is we convert it, or we call it transform it, into direct current. And then we convert into this direct current that our then devices and appliances can use. So for instance, when you go to charge your phone, right, that block that you have to plug your cable into, that block that then goes into the outlet, what it's doing is it's basically taking the alternating current from your wall outlet and then it's converting it into direct current that can then flow through the wire of your cable and go into your cell phone to charge it. So we're kind of basically using a combination of both. Right? The phone needs direct current, but we have AC current coming from the wall, so we need that block to transform it, to convert it to a different type. Now, this kind of back and forth debate that went on between Edison and Westinghouse and Tesla actually has like kind of a lot of very interesting history at play. So Edison, even though his approach wasn't as good scientifically, wasn't as practical as us using alternating current to set up our power grid, he basically tried to sway public opinion, and basically he attempted to scare people, and he tried to convince people that AC current was dangerous and we shouldn't use it, that we should instead use his own DC current setup. So he would do crazy things like he would electrocute animals in town squares using alternating current to try to scare people away from it. He took out this big ad in the newspaper where after the first electric chair death penalty sentence was carried out, they basically used alternating current to do that. Again, he basically tried to scare people away and say, you don't want this in your homes. It's deadly. It's lethal. But again, eventually, you're right, the science did win out. Right, we do have a safe way of transporting this alternating current, and it's a lot more feasible for us to power entire cities on our electrical grid if we kind of use this combination of alternating current and direct current.